Good morning, Geometry iPad Initiative students. This is Mr. Lane coming again at you from OHS High School. This is section 5.2 over bisectors of triangles. Make sure you read through the objectives. There's 2 of them this time. You can read through the why and make sure you answer number 5. You get to do a little drawing of a picture, so you might want to do that in Educreations. Make sure you're looking for that secret word of the day. 2 points for the first person to send it to me. Good luck on that. And let's go ahead and get to rolling on this. Concurrent lines. All concurrent lines are lines that intersect at a common point. So you could have 3 of them, 4 of them, 5 of them. Must have 3 of them for concurrent lines. But they all intersect at one point. That point is called the point of concurrency. That's the point at which they all intersect. All right. Then we have the circumcenter of a triangle, which is the point of concurrency of the perpendicular bisectors. So if we take the perpendicular bisectors of the sides, then we'll have the point of concurrency of the triangle, for the circumcenter of the triangle. Alright, the circumcision theorem says the circumcenter of the triangle is equidistant from the vertices of the triangle. So right here in red, we've marked the perpendicular bisectors of the sides. So that would mean that from there, green's not going to show up on that, that would mean that this would be congruent to this, which would be congruent to this. So we can mark this triangle A, B, C. Whoa, that's a bad C. There we go. And this would have to have a middle of P, and all those segments would have to be congruent there. They're equidistant from the vertices. Alright, what are the different types of triangles that could have a circumcenter? Does the circumcenters always stay on the inside? So what different types of triangles could we possibly have? Well, the one that was drawn in the theorem itself was an acute. What happens if we had let's say a right triangle? Let's try and take a look at that for a minute. There we go. Close to a right. So let's see, if I was to cut, actually let's do a little bit better job of that. Might end up with two videos this time. It's going to be rushed to try and get it in on one. Alright, there we go. There we go. There we go. So notice on a right triangle, it's almost pretty close to the side. A lot of times it will actually end up right there on that side on a right triangle. Let's try, do we got an obtuse triangle? Okay, so our obtuse triangle, let's see, right in the middle here, and I know I'm eyeballing it. We could do an actual construction, but I think we'll be alright. So notice on an obtuse triangle, when I bisect the sides, the point of concurrency is going to be on the outside of the triangle. So it could be on the inside, it could be on the side of a triangle, or it could be on the outside. Alright, which would allow us to circumscribe, which is a circle that contains all 3 vertices of the polygon, or in this case the triangle. So whenever we find the circumcenter, if we were to start a triangle that went through one of the vertices, it's actually going to encompass or hit all of the vertices. So that's what they mean by when they circumscribe a triangle, is they find the circumcenter and then they make a triangle going through every single one of the vertices of the triangle. Alright, let's work the first example here. It says DG, EG, FG are the perpendicular bisectors of the triangle. Find GC. Okay, well, not a whole lot of work for this one because the theorem, the circumcenter theorem, says that if I have the perpendicular bisectors and they intersect at G here, then whatever one of the distances is to the vertices, all of the distances is to the vertices, that same distance. So if this one's marked 13.4, then this one has to be 13.4 also. Alright. Regular geometry students, be doing those problems at this time. iPad initiative, yours should be connected to your Lumen lesson site. Alright, find the circumcenter of the triangle HJK with the vertices 0, 0. I'm going to go ahead and mark these vertices on the graph down here. That's H. Let's see, then I've got a 10, 0, which is J. And then I've got a 0, 6, 1, 2, 3, 4, 5, 6, which is K. Alright, one good thing about this is I know that the three perpendicular bisectors are all going to meet at the same spot. So I'm going to save myself a little bit of work in that, since I know that, if I could figure out where two of them intersected, I know that the third one would intersect there. The hard one would be the hypotenuse of this right triangle, to figure out where I need to draw the line this way, which I could count some rise over run, and then I could flip it and change the sign of it, so it wouldn't be that bad to figure out you know, the slope of it. And then I could use midpoint formula to figure out where the midpoint is and just start from the midpoint counting my rise over my run. Alright, but the easiest way to do this is to look at the two sides that form the right triangle, because if I counted halfway to 6, I'd count 1, 2, 3, and then a vertical line means that a line perpendicular would be a horizontal line. So, and then if I had the horizontal line down here, then I know a vertical line would be perpendicular to that. So let's see, if that's 10, I'd need to count 5. 1, 2, 3, 4, 5, and it would have to go straight up and down to intersect there. So they're going to intersect right here, which would be the circumcenter. So I need those coordinates real quick, which would be 5, 3. Okay. So a little shortcut, because we know that all three of them are going to be at the same spot. Looks like you got two problems right there. Good luck with those. And now we're going to start talking about the incenter of the triangle. The intercenter is the point of concurrency for the angle bisectors. And then we have another theorem here, which is the incenter theorem, and it says that the incenter of the triangle is equidistant from the sides of the triangle. So again, it looks like P is going to be our center point, and then it doesn't really matter which one we name, X, Y, and Z. And notice that now we bisect each one of these angles, and they're going to all intersect inside here, and then from that point it's going to be an equidistant to each one of the sides. What this allows us to do is, if we were to form a triangle that went through this side, it would also go through that point, and it would just connect at each one of those sides, where it's going to inscribe, it's pretty darn close right there, it's going to inscribe the circle inside the triangle. So inscribe would mean inside the triangle. Okay? Let's see, let's go on down to here. It says a circle inscribed in a triangle in this case intersects each line that contains a side of the triangle at exactly one point. So it is the circle inside the triangle. Alright, we have segment MP and segment LP are angle bisectors of the triangle. By the way, the secret word today is homecoming. Homecoming's the secret word today. Find each measure. Alright, so here we go. We've got this triangle drawn for us. Let's see, MP is an angle bisector, so we're going to go ahead and mark this congruent to this. And let's see, LP is an angle bisector, so that would mean that this would be congruent to this. Okay, find the distance from P to segment MN. Okay, MN. Okay, so is that even drawn in here somewhere? I guess it doesn't matter because it doesn't matter if it's drawn in here or not. We could probably draw it somewhere in here to, you know, it's going to intersect at this point here. But if this one is 5, then that means wherever I drew this one at, it's also got to be that 5 because all those distances are equidistant, which means they're the same distance. Alright, then we also got to find angle PMN, so it's the same as this angle, but I think we want to look at all the angles of the big triangle real quick because there's 180 degrees in the triangle. And we have 20 of them used right there, so I could subtract the 20, which would give me 160 degrees. And then it looks like there's 50, and this one has to be 50 over here, so that's 100 that's used. So that means that I have 60 degrees to use for this big angle here, which is bisected, so they're cut in half, so half of 60 would be 30 degrees. So it looks like this would be 30 degrees. Alright, there's regular geometry students, and then it looks like we have one more. I'm going to try and squeeze this in here. It says a city planner wants to build a new library between the school, post office, and a hospital. Draw and sketch and show where the library should be placed so that it is the same distance from all 3 buildings. So I'm going to cheat a little bit here. We're going to go ahead and get the just a triangle up here. Let's label one of them. Let's see, we got the school, we got the post office, and we got the hospital. So we want them all to be equidistant here. So to be equidistant, what we'll be looking for is that the perpendicular bisectors and where they all meet up at. So anyways, we're going to could do a construction and get this just right, but we're going to eyeball this. Looks pretty decent there. Looks pretty good. And this one's going to have to meet at the same spot here. Alright, that looks pretty good. So right here is where we should build the library. So that is equidistant to the school, the hospital, and the post office. All of these should be equidistant. So anyways, this is Mr. Lane. It's been another wonderful lesson. Hopefully you can pick up on the 2 main things, which is scribe and inscribe, or circumcenter and incenter of the triangles. So Mr. Lane signing off from OHS High School. Catch you next time.